Good morning, everyone. Let's open up our books, please, to the practice problems from the lesson way back on Wednesday dealing with exponential functions. The gist of what we learned on Wednesday of last week dealing with exponential functions is exponential functions are functions of the form f of x equals some base raised to the x. We said that the base must be greater than 0. So the base is not allowed to be negative. The base is not allowed to be 0. We said that the base was not allowed to be 1. Having a base of 1 would make no sense. It would just be, your function would be y equals 1 to the x, which reduces to y equals 1. And we took that a little bit further and said that if you were to visualize a number line that represents different values that the base could have, we said that the base could have any of those values represented by that red graphic. Cannot be 0, cannot be 1, must be greater than 0. We learned that this is called a decreasing exponential function when you have a base between 0 and 1, and this is an increasing exponential function when the base is greater than 1. We learned that what the deeper meaning of the base is that it's the number that y gets multiplied by regularly. So if you have y equals 2 to the x, every time x goes up by 1, y gets doubled. If you have y equals 0.75 to the x, every time y goes up by 1, every time x goes up by 1, y gets multiplied by 0.75. That's it, essentially, in a nutshell. Does anybody have any questions you would like me to go over from this section? It's been a few days, so you might want to take a look at your work.
Page 344.
Okay. So statistics indicate that the world population since 1995 has been growing at a rate of about 1.27% per year. Obviously, this textbook is old already. Estimates for the world population in 2011 is approximately 7 billion. When will the population be 9 billion? So we need to develop a formula to begin with here relating the population to the year. And this is a good example to use to learn something, which is that when you start talking about x, which is really going to be n for year, and y, which is really going to be population, you don't want to assign x the actual year. What you want to do is, if we're going to say that the population in 2011 is 7 billion, then we are going to use 0 for n and 7 billion. I'm going to write times 10 to the 9 because I just don't have enough room to write 9 zeros. So what we are doing essentially here, JV and everybody, is we are saying year 0 is actually 2011. So if, for example, we solve a problem now and we get n equals 5, I'm not saying the answer is going to be this, but if you solve something and you get n equals 5, we're talking about 2016. So n is not the year number, n is the years since 2011. And the reason for that is I've told you, I'm going to go with the B approach, which is on your formula sheet. I've told you that this general formula works as long as A is the initial amount. The initial amount of people, the initial number of grams of radioactive isotope, the initial value of a comic book, whatever it is. And that means that I can... Now, I think they have T on your formula sheet here, but it doesn't really matter. I can customize this and have population equals 7 billion. And you know what? Why don't we just put 7? Why don't we just say that this is going to be the population in billions? We can do that. Times, we're going to have to put in here for the base the number that things get multiplied by regularly. If you want to put 7 with 9 zeros, you can. We have to figure out what b is. Well, b is going to be 100% plus 1.27%. Because it says the population increases annually by 1.27%. So whatever it was at the beginning of a particular year, that's 100% of the population. We have to add 1.27%. So we get b equals 101.27%. But of course, percent, everybody, means divided by 100. Right? So we're going to have times 1.0127 raised to the n. And what we want to find here is this, I think. I'm going to eliminate the 10 to the 9 because we've just said the population is in billions in the formula, so I'm not going to use 10 to the 9. We want to know this. We would like to know what value of n gives 9 billion. In other words, we have to solve this equation, everybody, but we are still 4 or 5 classes away from learning how to solve that equation for n algebraically. We just don't know how to do it yet. The only thing you can do here, JV, is put nine in for y1. I shouldn't say the only thing you can do, but I think this is the quickest, cleanest approach. Put y1 equals 9, put y2 equals that, and find the point of intersection. And we can get a rough idea. I think we did this on Wednesday. We can get a rough idea of when that's going to happen by also peeking into our tables and seeing what's happening to the population. So, for example, if I just go into y, I'm going to go y2 equals 9 times 1.0127 raised to the x. And I'm going to look in my table right now. I'm going to start at 0 and go up by 1. I expect it's going to be at least a few years, but I'm going to start at 0 anyway. You can see that I entered in the wrong number, which should be 7. You can see that the original population is 7 billion, and it's going up, isn't it? So when I scroll down, I want 9 billion. Well, I can see that it's going to be about 20 years, which if I add that 20 years to 2011 gives me 2031. Thank you. But if you want a precise number, then we can do it graphically. I'm going to put 9 here. Now that I know it happens around 20 years, then I can go to my window settings and I can go up to, I might go up to 22 or 23. For my y, I need to go up. For my y, I need to go up to at least 9, more than 9, so I can see that line y equals 9. So I'm going to go up to 12. It's just a number. There's my y equals 9 billion, and here comes my model for the population of the Earth. I can find the intersection point. So it's 19.9 years. Now, I don't know the exact wording of this question. What is it we want? When will the population? Well, if I would say 19.9 years after 2011. I don't think we need to get into, let's see, 19 years after 2011 would be 2030. I don't think we need to figure out how many months 0.9 of a year is and start narrowing it down to a month and a day. I would just say 19.9 years after 2011. Is that okay? Good. Any other questions from any of the practice work? All right. So we're going to look at the next lesson in this unit, which is on page 5 of your unit handout. All we're going to do today is look at transformations of the basic exponential function y equals c to the x, or y equals b to the x. And then we're going to delve a little bit deeper into applications. Quite frankly, the first part of this lesson is something that you should know how to do already, because it's going to be dealing with a, b, h, and k being applied to y equals c to the x. And since you know what y equals c to the x looks like graphically, y-intercept of 1, horizontal asymptote on the x-axis, you ought to be able to tell me everything about transformations of that function. So as a warm-up, how would y equals c to the x be changed if it's transformed to some number multiplied by c to the x? And it's interesting where I put those brackets on the c. I could have put the brackets around c to the x, or I could leave it without brackets. Even if I were to write y equals a c to the x, it's implied that there's a multiplication in here, and your order of operations says you do the exponent operation first anyway. So we don't really need brackets. But what happens is the function y equals c to the x is stretched vertically by a factor of a. And I just want to make sure you understand that when we're talking about a here, we are talking about this a. You know, could we delve into more detail and say something like the horizontal asymptote will still be on the x-axis? Sure. Because every point on that asymptote will be invariant with regards to a vertical stretch. Could we say that the domain is still going to be any real number and the range is still going to be y is greater than 0? Yes. Could we say that the y-intercept is still 1? No. The y-intercept of this function will be a. Because don't forget, and I'm not going to do this in this detail with every part of the warm-up, but when you look at y equals c to the x, this is of course where c is greater than 1 because it's an increasing function. The y-intercept of that function is 1. We know that. So if I were to look at y equals some number times c to the x, assuming that number is greater than 1 as well, then what you're going to end up having is everything stretched vertically, and your old y-intercept of 1 will be multiplied by the vertical stretch factor. By the way, if that vertical stretch factor is between 0 and 1, which means it's going to squish the graph towards the x-axis, the new y-intercept will still be the value of that a. And to go even further, if a is negative and it reflects this vertically along with a stretch, the y-intercept will still be a. The y-intercept is always going to be a. So I didn't put up here that if a is negative, there could be a vertical reflection. Let's add that. And I didn't do a perfect job here because that stretched vertically by a factor of a. I suppose I could have put absolute value signs around the a. I probably should have. Because if a is negative, this goes way back to the first chapter. If a is negative, we're not going to say there's a negative vertical stretch factor. So another little observation we could make here. the y-intercept will be a. Not the absolute value of a. Whatever a is, that's going to be the y-intercept. The second part of the warm-up is not as rich with information. I mean, there's nothing really we can identify about the features of the graph after we include the parameter b, other than to say that if b is negative, there's a horizontal reflection. But more importantly, there's a horizontal stretch by a factor of the reciprocal of b. So I'm going to start abbreviating things here. I better not. So we have a horizontal stretch by a factor of the reciprocal of the absolute value of b. I'm not going to go into more detail here, like if b is greater than 1, then it's a compressive stretch. If b is less than 1, it's expansive. We don't need to get into that. And also horizontal reflection if b is negative. And if anything, everybody, this warm-up is merely a reminder of the things that we should know anyway. This is a review. Because everything that I'm writing here could be written for any function where x is multiplied by b. Right? I could, if I told you y equals log base 2 of x, and then I said, what does this look like in comparison to y equals log base 2 of x, whatever that means, because you don't know yet, you would say, well, it looks like this first function, y equals log base 2 of x, stretched horizontally by a factor of the reciprocal of the absolute value of b. And if b is negative, it's been reflected horizontally. Which takes us to the two translations. When we go from y equals c to the x to y equals c to the x minus h, it translates h units left if h is negative, absolute value of h units left, and the absolute value of h units right if h is positive. This will not change the domain or the range. Remember, c to the x, and I don't know that you need to draw this, I'm just pointing out some interesting features about this statement. C to the x, assuming c is greater than 1, y equals c to the x looks like that. So what would c to the x minus h look like? It would look like this graph, shifted left or right, depending on what h is. I do want to point out to you that there's an asymptote here, and this asymptote, if I shift the asymptote, which is a line that goes from negative infinity to infinity, I shift it left or right, it's still going from negative infinity to infinity. What is one feature of this graph that will change? The domain won't, the range won't, the asymptote won't. What will change? What's a feature of this graph that will change if I take that and I translate it left or right? Right? The y-intercept will change. We have no way of determining what the y-intercept is going to be yet by looking only at h, but we will learn the skills required. So this would be maybe y equals c to the x minus h. Finally, we get to c to the x plus k. Well, there is a translation of k units, and it will be up if k is positive, and it will be k units down if k is negative. For y equals c to the x, the asymptote is at the x-axis, which is y equals 0. For y equals c to the x plus k, the asymptote, the horizontal asymptote will be at y equals k. If k is positive, y equals k. If k is negative, y equals k. So again, that first 10 minutes here, we're just reviewing stuff that hopefully you already knew. By the way, your y-intercept is going to be 1 plus k. I don't know how important that is. But if your y-intercept of c to the x is 1, and I shift everything k, let's say k is 5. Well, then I'm shifting it up 5. The new y-intercept will be 6, 1 plus 5. Let's say that k is negative 5. Well, we're going to go from 1 for a y-intercept down 5, which would be negative 4, which is 1 plus negative 5. Again, though, if you have a horizontal translation, all bets are off. You cannot start to figure out y-intercepts with horizontal translations. All right, describe the transformations needed to transform y equals 3 to the x into 2 times 3 raised to the x minus 4. Well, this is easy. There's a horizontal stretch by a factor of 2, reminding you, of course, that on a written response you would actually write that out in words. And the reason for that is the parameter a is 2. We have a parameter of h of 4, which means there's, after this happens, a shift of 4 units to the right. So that's all that happens. We're okay with A? All right, now what we have to do is sketch these. And I'll warn you right now, every time I teach this course and I fine-tune my notes, change my notes, I always think, geez, Paul, just take these examples out. Graphing it is frustrating. It's frustrating for me and it's frustrating for students. But I still believe that you learn something by graphing these. Okay? So what we want to do now is sketch graphs of y equals 3 to the x and y equals 2 times 3 to the x minus 4. And then we're asked for some other information. So first of all, understand that your graphs do not have to be perfect. And I pulled this basic grid from a diploma exam where they had a very similar question. And when I first saw it, I thought, well, that's kind of dirty. We have a base of 3, and look how the vertical axis is scaled. It's scaled horribly. So our graphs are not going to be perfect. The first thing we want to do is start off with y equals 3 to the x, which I'm going to graph in green. I know that 3 to the x has a y-intercept of 1. And even that, putting 1 on there, which is 1/5 of the way from the origin to the first mark, where 5 is tough for me. It might even be actually easier for you because you can use a finer point. Remember that a base of 3 means when x goes up by 1, y gets tripled. So when x is 1, y will be 3. When we take 3 and multiply by 3 again, we get 9. So when x is 2, y is 9. And we can triple that again. When x is 3, y is 27. And I think if we triple 27, we get 71. I don't know. My brain is not warmed up yet. 27 times 3, 70, 81? 81. Do we have room to put 81 on here? No, we don't. So that's as good as we can get here. You should do your best to neatly draw an asymptote. I'm not going to worry about different colors for asymptotes. That's the asymptote for y equals 3 to the x. So now you have to sketch this. And I wouldn't be overly ambitious. If you can get a sketch that looks like this, that's fantastic. You don't need any finer detail. And I should label that because, I mean, I can see it's green, but you may not have different colors, so we'll make sure we label it in our notes. So now what I'm going to do is I'm going to stretch this vertically by a factor of 2 and shift it 4 units to the right. Now, I think it's more troublesome for us to sketch it after a vertical stretch by 2 and then as well sketch it again after then shifting it 4 to the right. I think we're able to handle 2 steps at once. But I also want to make a point to you that if I stretch this vertically by a factor of 2 and shift it to the right, that asymptote is not going to move. It's still going to be asymptotic, and that actually is a word, I looked it up one time. It's still going to be asymptotic to the x-axis. So what am I going to do? And I will do this one in red. This is y equals 2 multiplied by 3 to the x minus 4. Again, where you put that set of brackets is really unimportant. You don't even need the brackets there. So I'm going to take this point, which is at 1. I'm going to stretch it vertically by a factor of 2, which will put it at 2. And then I'm going to shift it 4 units to the right. We could, of course, do this with mapping and taking the coordinates of the original point and using a mapping expression, but I think that's more trouble than it's worth. Again, doesn't have to be perfect. I'm going to go to my next key point, which was at 3. That had a y coordinate of 3. So if I stretch it vertically by a factor of 2, it then becomes a y coordinate of 6, and I'm going to move 1, 2, 3, 4 to the right, and it will be at a y coordinate of 6. I can go to another key point. This key point had a y coordinate of 9. If I stretch 9 vertically for a y value by a factor of 2, it becomes 18, which is 3/5 of the way between 15 and 20. And I shift it 1, 2, 3, 4 units to the right. And I might even go so far as to say that that's probably good enough, but we can do that last point if you want. This had a y coordinate of 27. Stretched vertically by a factor of 2 takes us to 54. Help me out, please. 54 is 27 times 2? Yes. 54 is 1 less than 55, and I shift it 1, 2, 3, 4 to the right. So what I end up with is this, roughly. And you can see that I'm not even really too concerned about the fact that I missed every point except for the first one. I don't care. It's steeper. It's clearly steeper because it's been stretched vertically by a factor of 2. It is still asymptotic, and I feel as though I have room to put in that arrow on the bottom. I don't think I really had room to do it with the green one. And this would be, that is kind of bothering me. I'll try again. There we go. You don't have to erase it. It doesn't have to be a work of art. I don't think you would ever see this on a diploma exam, having to physically sketch this. Usually the graphs we sketch with regards to transformations are straight line graphs, like the letter W or something. So this is y equals 2 multiplied by 3 to the x minus 4. What were we asked for? The domain and range of the new function. So I'm going to get rid of this so I have room to write this. Well, the domain of the new function is still x is any real number, and the range of the new function is still y is greater than 0. There is still no x-intercept. And in terms of the y-intercept, we don't really know how to find this algebraically, because what you would have to do, and I'm not sure you want to write this down, but if you wanted to find, no, you know what, I take it back. We can find the y-intercept. You just let x equal 0, right? The y-intercept is where x equals 0. So let's just put 0 in here. We'll get y equals 2 times 3 to the 0 minus 4. So 0 minus 4 is negative 4. 3 raised to the negative 4 is 1 over 3 to the 4, which is 1/81st. It's 2 over 81. And I saw a bunch of you put it into your calculator. Is that what you get in fractional form, 2 over 81? Like, that's tiny. So the y-intercept is 2 over 81, or whatever number that is. I can't imagine what that number is. Any questions with that first example? A or B? All right. So number 2, what are the transformations involved in going from y equals 3 to the x to y equals negative 1/2, 3 to the 1/5 x minus 5? We're going to graph this in a second. It's going to be a beast to graph. But there is a vertical reflection. If this were a written response question and I wanted to really impress the marker, I would say across the x-axis, but it's not, and I don't. There is a vertical stretch by a factor of 1/2. Again, you wouldn't abbreviate things on a written response question. There is a horizontal stretch by a factor of 5. And then there is a shift downwards of 5 units. This is all because A is equal to negative 1/2, B is equal to 1/5, and K is equal to negative 5. But again, these are things that we should know already. Right? This really has very little to do with the fact that it's an exponential function, other than the fact that you have to wrap your head around how A, B, H, and K fit into 3 to the x. So we want to sketch these. So let's sketch 3 to the x again. 3 to the x has a y-intercept of 1. This grid that you're given this time, each square going up is 2. And, oh man, I hate it when this happens, but this is from your text and the diploma exam does it too. The horizontal is scaled that way as well. So it has a y-intercept of 1, and then if you go over 1 for x, it gets multiplied by 3 because the base is 3, which means at 1, which I'm just going to mark right here, this is 1. The y-coordinate is 3. At 2, which is here, and I'm going to erase these vertical lines, I'm just indicating where 2 is, we triple 3 and it becomes 9, which is here. At 3, which is halfway between 2 and 4, we triple 9 and get 27, 24, 26, and I just have room to put 27. And I would, mainly because I don't really feel that confident in drawing a curve, I wouldn't worry too much if you drew a curve through there. You can if you like, but it's so steep. And depending on your fine motor skills, I mean, you people that take art, you might be better at this than me, but it gets, he erases it. It gets difficult. I'll give it a shot. I'm not too happy with that, but that's okay. I kind of went off the rails there in between the third and the fourth points. So now what we're going to do is take those points, and in fact, I'm not even going to have that on there. I don't care. I'm just going to leave the points. I'm going to take those key points one at a time and apply all of the transformations. I'll do the new one in red. So what are we going to do? We're going to reflect that vertically, which means it's going to be below the x-axis. Then we have to stretch it vertically by a factor of 1/2. Oh man, it's going to be really, really close to the x-axis. It's okay. We're not committed to drawing this point just yet anyway. Just realize that it is a half of a unit below the x-axis. Okay. And then we're going to stretch it horizontally by a factor of 5. Well, that doesn't do anything, does it? Because it's on the y-axis. And then we are going to shift it 5 units down. Now, here comes the important point. This red point right now is half of a unit below the x-axis. But the x-axis is the horizontal asymptote. And when I shift this down 5 units, that horizontal asymptote, which was here, is going to be here. And that red point, which was 1/2 of a unit below the x-axis, is now going to be 1/2 of a unit below that horizontal asymptote. So we'll stop for a second here. Double check. Did we take into account the reflection vertically? Yes. Did we take into account the vertical stretch by a factor of 1/2? Yes. Did we stretch it horizontally by a factor of 5? Yes, even though that didn't do anything. And then we shifted that point down 5, but at that point I said the asymptote has to go down 5. So now we're going to repeat that process with these other points. This one, I mean, you have to kind of be aware that that point that I've just labeled there is at 1, 3. You have to be aware of the numbers we're dealing with. So I reflect it vertically. It's going to be at 1, -3. I stretch it horizontally by 1/2, which means it's going to be at 1, ½ of -3, which is -1.5. But then we have to stretch it horizontally by a factor of 5. So it's going to be over, it has an x-coordinate right now of 1, times 5, it will be at 5. But remember, at this point in time, and this is a lot to take in, that point right here is 1.5 below the x-axis. So when we shift it down, it's going to end up being 1.5 below the asymptote. I don't even need to look at what that y-coordinate is. I just need to know that this distance will be below it, below that asymptote. And you know what? At this point in time, if you wanted to, and you drew this, I would be very happy. I don't think we need to go to more points. It is stretched out quite a bit horizontally. It is also visually stretched out even more horizontally because we stretched it by a vertical factor of 1/2, and we can answer all of the questions at this point in time. The domain is x is any real number. The range is y is less than -5. I'm just going to throw this out to you. I'm not going to write it down. Your range of these exponential functions of this form will always be, y is greater than k or y is less than k. And it's going to be y is greater than k if a is positive, because then it goes up. It's going to be y is less than k if a is negative. By the way, if you were to take this next point and do all of that, I'm not sure it would land on this curve. It might be further to the right, but you get the idea. No x-intercept. Y-intercept, this is again where x is equal to 0. So put 0 in here for x. What are we going to get? We are going to get 0 times a fifth, which is 0. 3 to the 0 is 1, times a -1/2 is -1/2, minus 5 is -5.5. Of course it is, because it's half below the asymptote, and the asymptote's at -5. Any questions with number 2? All right. So now we're going to dive in with both feet to this formula that's on your formula sheet. So this that's in the box is on your Math 30-1 formula sheet. I've never liked the fact that they call the variable on the left y, but the variable on the right is not x, it's t. Okay, I get it that we use it 99% of the time where x is time. But the thing that I want you to understand, very important, is that this and this are variables. They are the things on the graph. Whatever you have in the position of y is the thing that's plotted on the y-axis. Whatever you have in the position of t is plotted on the x-axis. Everything else is a parameter. So when I solve a problem dealing with the value of a rare magazine, A, B, and P are parameters that are unique to that problem I'm solving. When I solve a problem dealing with investment of money into a compound interest account, A, B, and P are numbers that tell me about that problem. So, please, when you're using this formula, even though it's in this lesson, we do not think of stretches here. Don't think of stretches. Don't think of A as a vertical stretch factor. Your textbook will do that. Your textbook will also use P as some kind of stretch factor, but I'm saying it's confusing. What A is the initial amount. What B is, I often call it, and I don't know if I typed this out, B is the factor of change. It's what y gets multiplied by regularly. And P is how long it takes to happen. Do you remember, I know Wednesday was a long time ago, we did that problem with radioactive decay where it was 15-day intervals on the bottom? We had to do that because all we learned was that each time x goes up by 1, things would get multiplied by that number. And that's because, for example, with that problem, the half-life was telling us something was being multiplied by a half regularly, but it wasn't being multiplied by a half every 1 day. It was 15 days. This P allows us to incorporate that 15-day thing in there. So P is how long it takes to happen. In the problem that JV asked about at the beginning of class, P would have been 1 because it happened every 1 year. And that's why I assigned those problems last week, because you couldn't do it otherwise. So now let's take a look at this question. Radioactive element americium is used in smoke detectors. It has a half-life of 432 years. So now you need to remember what I told you about half-life from Wednesday. In case they don't tell you on an exam, half-life is the period of time it takes to get multiplied by a half. So when we say that it's multiplied by a half every 432 years, and the symbol for years is A, you're being told that this is B, the base. It's got nothing to do with A, B, H, and K. B here on your formula sheet is the base. And this is P, the period of time it takes for it to happen. What's the equation of the exponential function? Well, we already have B and P. Let me make it a little more visual for you. We already have B and P. If your formula is, from your formula sheet, A times B to the T over P, then we're only missing one more parameter, A. Well, A is the initial amount. Initial amount means what you start off with. And that means the answer to this question is y equals 200 grams times 1/2. I'm going to write it as 0.5 raised to the t over 432. That's it. If I said to you, how much will remain in 600 years? In fact, I'm going to add that on paper here. We've got lots of time today. If I said how much is left after 600 years, all you would do is you would take the formula and put 600 in for t. So we'd take 600. This is, just I'm a product of my education and having a scientific calculator. I do it this way. I go 600 divided by 432. Of course, not there. 600 divided by 432. Then I take 0.5 raised to that answer. Then I multiply by 200. Do you get the same number? I don't think that can be right. I only multiplied by 20 instead of 200. When you use 200, you get 76.37. Okay. So it's just a matter of putting that number in. If I said to you, what do we start off with? 200? How many years does it take to get down to 28 grams? Then you're going to be solving this equation. 28 equals 200 times 0.5 raised to the t over 432, which you don't know how to solve algebraically. And quite frankly, everybody, I hope that when you do learn how to solve it algebraically, you'll appreciate that it's simpler to solve it algebraically than graphically. Graphically, you got to deal with goofy scales. But let's do this. I'm going to put in for y1, 28. For y2, I'm going to put 200 times 0.5 raised to, and I would need to put a set of brackets for that t over 432. What am I going to do for my window settings? Well, I know that this is a decreasing exponential function because the base is between 0 and 1. The base is 0.5. I know that it starts at 200, so it goes down, which means my vertical range is going to be between the x-axis and 200. Well, that's helpful. I'll go 220. Now, what about x? Yeah.
You typed 20 instead of 28. Also, it starts at 200 micrograms.
Also what?
200 micrograms.
Oh, it's okay. So when I said grams earlier, it's micrograms. That goofy Greek letter mu means micrograms. Thank you. So I'll fix that first. And now back to what I've entered. So I want to get down to 28 for a mass. So I'm going to go to my table. Table set. Start at 0. And go up by 1. Because I don't know. Well, I kind of have an idea, but I'm thinking physics here. If I go to my table, look at this. Oh, man, I'm going to be scrolling for a long time, aren't I? It's clearly not a few years, so maybe I have to reevaluate and start at 0 and go up by 50 years. You could try 10 first. I think 50 would be maybe a better move. I want this to decrease to 28. Okay, well, now I don't mind scrolling for a little bit here. it's looking like, around 1,200 years, roughly. So in my window setting, maybe I'll go up to, 1,400. If I've done everything right when I graph this now, I should see the 28. I should see my declining or decreasing exponential function, and then I can find the point of intersection. Go to my Calculate menu and choose Intersect. First curve, second curve, enter for a guess. So about 1,225 years. Any questions with either of those two? Made-up examples. All right. There's a list of practice problems that can help you out here. If you're asked to graph, I'm not a big fan of that. I don't think you have to graph anything.